But first of all, we need to take a step back and ask, what does it mean for a brain to be shaped by experience? What is being shaped? So let's just think about the difference between computers and brains. So at some level, this is a very obvious topic, and what I say is kind of obvious, but there's a very important point here. So this child is looking at this apple, and just like you are looking at the screen right now. So what does it mean for the child to be taking in this image of the apple? And what is the difference of a computer having a JPEG image stored in its hard drive? So here's a JPEG image of an apple. It looks like an apple that might be on your table and that you can eat, but you know it's different. So you know that this is an apple, but that is a concept, right? Actually, the computer doesn't know this. If you zoom into this image of an apple on your screen very closely, it will start to get pixelated like you see in these images on the right. And ultimately, it will just be different bands of red, green, and blue at different intensities. And by manipulating these intensities, you can create any image, or at least a simulation of an image. So yeah, anything you see is a simulation in that way. So all the computer knows is the numbers that specify the intensity of these red, green, and blue values. And so you can, of course, as you know, you can represent this image of an apple just as a string of zeros and ones. So there's no concept of an apple as such. There's just information, right? The difference with what the computer can see in scare quotes and what the human mind grasps is this kind of higher order structure that the human mind creates. So in psychology, this has been called Gestalt, which is German for shape or form. And so, for example, in this cross here on the left, is the middle symbol a 13 or is it a B? Which do you see? It probably depends on the context, whether you're reading from top to bottom or from left to right. And if you saw it in only one context, you would just think it's a B. But it's really the human mind that is doing this complex computation where it's trying to understand the context and then changing what you actually see based on that. Same for the pentagon on the right. Or is it a pentagon? There's actually no kind of sure way in which you can say there's a pentagon that is logically valid, because all there is these incisions in the circles that imply the presence of a pentagon, right? But it's very hard to unsee the pentagon because this is your mind filling in the lines, and you see the line even when it's just white on white, as I think you can see yourself. So it's really this remarkable feature that psychologists in the early 20th century discovered, that it's really not like a pixel model of vision. The mind is creating these forms of organization or gestalts. And it's clear that the mind must be doing something like this, just based on the poverty of the information that is coming in. Of course, there's light, there's compression waves of air as sound. You have the taste of an apple on your tongue. There's many different stimuli coming in to the brain, but it's really on these kind of specific surfaces. So let's just stick to vision for now. So on the right is a section of the eye. So your eyeball on the back is lined with a layer of cells called the retina. And then these retina, the retina is lined with photoreceptors. So this is the kind of cell that responds to photons, and it's a really remarkable thing. But so basically it's kind of like so it's the photosensitive layer on the back of your eyes that works kind of like a pinhole camera. And then this information from the photoreceptors are sent through the optic nerve to your visual cortex eventually. So here's a neuroscience diagram. So this is it's called the ventral visual stream. So this is one of the processing streams of the visual system. And so again, you see the eye here. It's going through a structure called the LGN and then into V1. V1 is called primary visual cortex. And by the time the information from the retina, which is kind of like pixels, it's points on a surface, reaches V1, the information gets transformed into these oriented lines you see on the bottom right here. So each of these squares in this 10 by 10 matrix represents what one cell in your V1 part of the cortex would be seeing. So these oriented lines. And then now this information gets processed as it goes up to V2, V4 into this area called inferotemporal cortex, which is around your ears. And then by that point, you're able to see the concept of an apple because you have cells that respond not to just lines that combine together. Even these contours can make an apple, but that's just kind of a surface image. But once you get to IT, AIT, CIT, PIT, there are cells that respond to an image of an apple, a caricature-like drawing of an apple, even the word apple, written or spoken, it will respond to all of these things, but not to an orange, whether it's written or a photograph or a drawing. So it is specifically targeting the idea of an apple, and this is just in vision. So the visual system is doing this remarkable operation where it's creating these complex representations, right, out of just these pixel-like stimuli that are ultimately just coming from photons impinging on your eye. But of course, it's not just transforming input into a decision of whether something is an apple or a pear. Everything that you do is mediated by the brain in some form or the other, unless you're talking about purely mechanical reflexes that just go through your spinal cord, or just mechanical things that you can do with your muscles. But so, for example, is this situation? I watch a film or I watch relatives fighting. Is it just or unjust? Okay, now this seems a very complex judgment compared to apple or pear. But of course, this is also done by the brain. It's not just vision. There's a lot of social information. Also, you're getting information from your internal organs. When you say gut feeling, this is actually correct, because there are parts of your brain called the insula and other areas that is getting information from this, and in a holistic fashion, you're judging, is this just or unjust? And it can be a very strong feeling, right? It's not just binary, deciding is this A or B. Also, how dangerous is the situation, or how welcoming is it? So your brain is also computing this based on all the inputs that it's getting, not just in real time, also the inputs that it's getting in the past and that it's expecting in the future. So it's integrating across time as well. Also something like how funny is this? Okay, it's kind of a strange question. You hear that, whenever you ask, is this funny? It becomes unfunny, right? And you might say, okay, I never compute in my mind whether something is funny. I just see Ronnie Chang, or I see Mr. Bean and I find it funny. I laugh. But actually, it only seems that you're not really computing this because it's so fast. Just go back to this diagram. You see on the right here, there's a column called latency. By the time the photons impinge on your retina to the time that you grasp the concept of an apple, it's only 100 milliseconds. 100 milliseconds is 10% of a second. So all of these computations of the brain are very fast. So something is funny before you maybe even before you really see it in a strong sense. So what the brain is doing in the sense is building up what we might call representational complexity. You're taking just these, what is essentially the same as ones and zeros, just with photons or other sensory modalities, and you're creating these complex representations like, is something just, is it dangerous, is it funny? So here are a few points that we can take away from this discussion. The most important thing is not the information coming into the brain, but rather the neural representations that are formed through learning. And a new concept is literally a new way of seeing the world. Computers store surface information, but typically cannot and have no need to interpret this information. AI does interpret information like humans. So, the most recent AI algorithms, you might have heard of deep learning. These are different from just storing something on a hard drive because they do infer. But AI interprets for the sake of interpretation, whereas humans interpret for the sake of action, planning, and exploration of new sources of value. So just look at something like this Greek proverb: a society grows great when old men plant trees whose shade they know they shall never sit in. You might have heard this proverb before. It's kind of generic, but I think we can all agree that it captures some kind of wisdom that is worth learning. And in a society that has not accumulated any wisdom from the past, maybe they will not have this idea. But if you translate this into machine code, into just a binary, the string on the right with zeros and ones is the same information as the letters on this left panel here. But of course, in the strings of zeros and ones, there's nothing about society. Just looking at this, there's no notion of society. There's no notion of what it means for society to be great. There's no, on the left, for example, death is implied in the left, right? But there's nothing about that in the right. So actually, just the information itself, there's not much in there. When you read the text on the left, it seems like the wisdom is in the text itself, but actually it's you that is interpreting the letters, and through that building up the word, and then you're building up the representation of a sentence. And so it's really you that is seeing the thing that corresponds to wisdom in the information. The computer knows nothing about this. Just like how the computer doesn't see an apple, it just sees zeros and ones. The computer doesn't see society. It doesn't see the notion of plant trees. It just sees zeros and ones, right? So if the goal of a human learning is to build up these complex representations, now we can start to see what it means to learn subjects in the humanities. So whether it's history, music, literature, and actually even something like physical education. So all of these are forms of learning complex representations. So in history, you're probably not trying to teach just these individual events or years, even though it might seem like that to the student. What you're trying to convey over the long term is the complex forms of organization and the way human societies behave, which cannot be reduced to individual events like this person murdered this person. Same for literature. You're not trying to teach these fancy words, even though they might be interesting in themselves. What you're really trying to do is using these words to convey these more complex situations, human drama, human emotion. And again, so it is like extracting the concept from a pixel almost, just in a different way. Same for musical notes and kind of compositions. And so these kind of actions too, like you see in the Olympics, these are interesting because it's sort of the other way around. Just like with vision, you have to start with pixels and then you end up with these very complex representations. With athletes, you start with a complex representation of movement in your brain, in the frontal areas of your brain. And then ultimately, all you can do is control individual muscle twitches. And so how do you control individual muscle twitches to get something like these amazing performances that you see on the high jump? It's by forming these complex representations in the motor system over time. So today I focused on vision, but it's really a whole brain principle. So given that learning is about building these complex representations, and these complex representations are a function of the information that you're getting from the environment, what does it mean that the information is changing? The information ecology has changed drastically in the last 20, 30 years. And so the rest of the talk will focus on what this means for the brain.